let's run through some parameters that are typically very important for terrestrial ecosystems. If you would want to think about measuring quantities from space or modeling the ecosystems, then you need to be aware of these important quantities. Measurement of vegetation or primary production or terrestrial biosphere from space, as we said before, depends on basically the spectral signature. So all the shortwave radiation coming in is not used for photosynthesis. There is something called photosynthetically active radiation, or PAR, PAR, and what is measured for estimating the biosphere is something called fraction of absorbed PAR. So not all of the PAR gets absorbed as well. So the technique has been used for taking the radiant signatures coming from the biosphere in a satellite or drone or airplane or whatever else, and convert it into some measure of how much primary production is happening. And primary production is in some way just the amount of carbon that's getting fixed. In other words, going from inorganic carbon into organic carbon. Okay, so obviously this is a ratio, it's a fraction, so goes from 0 to 1, and where there is high values, there is high photosynthesis or photosynthetically active PAR radiation being taken up. So you can see the various regions where you expect rainforest, Amazonia, Central Africa, and the maritime continents, but it's also going to measure everything that is green, like crops and so on. So that's the main technique used in estimating things, and this is just measuring chlorophyll radiance. So as we said, chloroplasts absorb in the red, and so you can measure associated green that is being reflected by the photosynthesizers to monitor the terrestrial and marine ecosystems here, showing the seasonal cycle that we looked at before. We talked about the seasonal migrations of the ITCZ and the associated photosynthesis, and also the waning and waxing of the upwelling as well as river runoffs. Here you have Congo Zaire River coming off, Amazon, Orinoco, Ganga, Brahmaputra, Irrawaddy, and so on and so forth. Okay, so all sorts of colored dissolved organic matters get detected here. For example, Lake Victoria is very clearly seen in here, and also the high latitude seas. We talked about the spring bloom and so on and so forth. Okay, the seasonal phasing of the fraction of absorbed PAR can be also mapped using the data. Where it's white, there is no data, snow cover, ice cover, and so on. So not enough vegetation exposed to measure PAR. But you can see how the seasonal cycle works in various places. So you can see July maximum here, which means ITCZ is overhead during July and photosynthesis and vegetation is maximum. This could be monsoon agriculture as well as Western Ghats vegetation. Amazonia has a strong seasonal cycle, and so on and so forth. So you can see the granularity of the data as well. So you can even see where there is lots of agriculture, forests, and other vegetation types versus where there are just deserts. Okay, so this is a very useful quantity as well as far as terrestrial ecosystem is concerned. And this is the seasonal concentration of the FA-PAR. And obviously deserts, Amazonia is, I don't know why this is white here. I should be careful. Um, Let me think about that and get back. So somehow this is measuring the power concentration and not fraction of absorbed power, I suppose. Okay, growing degree days is important because this is, for example, changing with global warming, because now winter ends early. The length of the day doesn't change with global warming, but the temperatures allow the growing season to get longer. As soon as minimum amount of radiation is available, if temperatures are warm enough, you can drive growing seasons. So growing degree day is defined as the mean daily temperature, average of daily maximum and minimum temperatures above a certain threshold base temperature accumulated on a daily basis. Okay, so number of days where you have the temperatures, average temperature above the minimum threshold needed to drive photosynthesis. So that's another measure of tracking biospheric response, let's say, to global warming. Okay, with warming you expect growing degree days to change and increase over most of the places. So it's always a question of whether temperature increase and precipitation increase actually lead to crop yield increase, or are they thresholds beyond which temperature becomes actually too warm and then crop yields begin to fall off. And there is also some evidence that pollution like ozone can have very heavy negative impacts on crop yields, for example. Okay, that's not the same as for trees and forests, so we have to be careful. We will look at a map of something called moisture index. It's defined by Thornthwaite in 1948 climate classification. It's an overall measure of precipitation effectiveness for plant growth that takes into consideration the weighted influence of water surplus and water deficiency as related to the water need by the plants. And they vary obviously according to the season, because in the dry season actually plants can manage the water efficiency quite well. So that's what this means. There is also humidity and aridity indices involved here. Basically they are temperature dependent indices of the humidity above the threshold, and aridity means you are below the threshold. So it's a combination of those things for a given station, which is some index here, which is the moisture index. S is the water surplus, D is the water deficiency, so you have humidity and aridity there, and N is the water need. So you need to know the water need of specific plants or plant types, and then you know the humidity index, aridity index, and create a moisture index out of that. So this is the moisture index going from 0 to greater than or equal to 2. So in that formulation, if you have water surplus, then obviously you are going to get moisture index. So in most places the moisture index ranges over 0 to 1, and there are few places like these here and the heavy rain regions of the Amazonia and Central African forest, but obviously there is no vegetation here, so that doesn't have much meaning in this terrestrial ecosystem context. So that's another index to watch out for, because we are always looking for how soil moisture and drought severity and the growth rates of droughts, duration, frequency, intensity of droughts is going to change with warming. So it's not necessary that always precipitation itself is the only cause for droughts. You can have warm temperature and soil moisture loss driving the droughts as well, which happens a lot in California, for example. Okay, this is the mean temperature of the coldest month. Temperature is obviously a very strong requirement for plants. There is a temperature dependence of the photosynthesis as well. With warming, it can grow. The photosynthetic rates can increase, but beyond a threshold they can begin to wilt and have stress. Okay, so this is the degrees for obviously much of the global south has warm mean temperatures during the coldest months. during the coldest months. Okay, 28 degrees centigrade in deserts and so on. And if you go on the Himalayas and to the northern latitudes here, you get the very cold temperatures, obviously. Okay, so I won't spend too much time on it. The other thing we need to know is that there are different pathways of photosynthesis called C3 and C4, and CAM plants. They have certain differences, but C3 plants are essentially most plants. C4 plants are tropical grasses like corn and sugarcane, and CAM plants are succulents like and pineapple and agave, which is kind of a cactus. So C3 and C4 basically differ in the way they fix carbon in the Calvin cycle. So these use rubisco, and this is fixed carbon in the cytoplasm. So they do a different pathway, and that is the number of CO2 molecules involved. CAM plants fix carbon at night only and fix it to organic molecules. I don't want to go into too many details, but essentially these matter because C3 plants respond well for I think high CO2, whereas these do better when there is low CO2, and they also do better with warmer temperatures. Okay, so they have evolved under different conditions, and they have optimized different things. Energetically also they are different requirements in terms of fixing carbon into organic molecules. But under global warming we want to understand how C3, C4 and CAM plants respond to warming and changes in precipitation and so on. Okay, that's why we look at these specific things. We will get into some details later on the projections, but this is just kind of an introduction to the topic here.